I was sitting in a coffee shop this morning and I just kind of looked around. It
Uh-huh.
was quiet, but it was also incredibly busy. Everyone just heads down, tapping on glass, clicking on trackpads, staring into these glowing rectangles.
Yeah.
It's wild when you actually zoom out and look at us as a species right now.
It really is. We are tethered to them completely.
Right. We spend 8, 10, maybe 12 hours a day interacting with these machines. We press a key marked P, and a pixelated P appears instantly. We click send, and a document just flies to the other side of the planet. It really feels like magic.
It is the closest thing we have to actual magic.
Always.
But the problem with magic is that it relies on mystery.
Exactly. And that's the thing. For most of us, the computer is a black box. We know how to use it. We're professional users.
Oh, yeah.
We can swipe, scroll, and type faster than we can think, but we have no idea what is actually happening inside that box to make the P appear.
And that's a vulnerable place to be. We aren't anatomists. We're just passengers. And considering this machinery runs our entire lives, our banking, our communication, our entertainment, it feels like we owe it to ourselves to understand the engine a little better.
And that is exactly the mission for this deep dive. We've gone through a stack of materials on the overview of computers and programming languages. We are going to deconstruct the machine. We're going to peel back the layers from the hardware you can kick to the code you can't see and try to understand the psychology of the computer.
Psychology is a great word for it, because computers do think, in a way.
Right.
But their thinking is so rigid, so specific, and totally unforgiving. Once you understand the rules they play by, the magic kind of goes away, but it gets replaced by something actually cooler, a real appreciation for the logic.
So let's start with the body, the anatomy. The source material breaks down the hardware into a few key players that everyone has heard of but might not fully grasp. We've got the CPU, RAM, the SSD. It sounds like alphabet soup.
It does, but if we map it to something human, it makes perfect sense.
Yeah.
The source uses this great analogy of an office.
Oh, I love this analogy. Let's set the scene.
Okay, so picture an office. Sitting at the desk is a worker. That worker is your CPU, the central processing unit.
Okay.
This is the brain of the operation. The CPU is the component that actually does the math, makes the decisions, and executes all the logic.
So the faster the CPU, the smarter, or at least faster that worker is at the desk.
Exactly. A better CPU is like a worker who can do calculus in their head instantly versus one who has to, count on their fingers.
Right.
But a brain needs a place to work. A worker can't just hold everything in their head. They need a workspace.
And this brings us to the memory.
Right. In our office analogy, looking right at the worker, hanging on the wall, is a whiteboard. It's your random access memory.
The whiteboard. I like that.
It's immediate. It's right there. When the CPU is working on a task, let's say editing a photo or running a spreadsheet, it puts all the data it's currently using right on that whiteboard. It's fast to write on, fast to erase, and fast to read.
But there is a catch. And this is a concept the notes highlight heavily: volatility.
Yes, RAM is volatile. This is crucial. Imagine if the office building loses power. The lights go out. In our analogy, when the lights go out, that whiteboard gets wiped completely clean.
Poof, gone.
Everything you were working on, that unsaved Word doc, that open browser tab, if it was only on the whiteboard, it just doesn't exist anymore.
That explains the sheer panic of a computer crash when you haven't saved your work. The data was just floating in volatile memory.
Precisely. It hadn't been filed away yet. To keep things safe, you need non-volatile memory.
Yeah.
That's your storage, your SSD, solid-state drive, or the older hard disk drives. In the office, that is the filing cabinet in the corner.
Okay, so the filing cabinet is distinct from the whiteboard.
Very distinct. The filing cabinet is slower. The worker, the CPU, has to physically get up, walk over to the corner, open the drawer, find the file. It takes time.
Sure.
But, and here's the key, it is permanent.
Yeah.
You can turn off the lights, go home for the weekend, come back 10 years later, and the files are still in that drawer.
So when I hit save on my document, what I'm actually doing is telling the worker, hey, take this off the whiteboard and put a copy in the filing cabinet.
That's it, exactly. And connecting all of this, the worker, the whiteboard, the filing cabinet, is the floor they stand on. That's the motherboard. It's the circuit board that lets the CPU shout orders to the RAM and the hard drive.
Okay, so that's the body. We have the brain, the short-term memory, and the long-term storage. But a body without a mind is just a paperweight. We need to talk about software. The source makes a distinction here between system software and application software.
Right. Think of this as the hierarchy of control. At the bottom, closest to the hardware, You have your system software. This is your operating system kernel, your file explorer. These are the heavy lifters. They manage the hardware.
Yeah.
They keep the house in order.
They're the office manager.
Exactly.
Hmm.
They make sure the worker isn't trying to write on the whiteboard and the filing cabinet at the exact same time. And sitting on top of that is the fun stuff, the application software.
The apps. Spotify, Chrome, Microsoft Word.
The stuff you actually care about. But here's the thing. These apps generally don't talk to the hardware directly. They act like VIPs. They ask the system software to do the dirty work for them. It's all layers of translation.
So we have the machine and we have the instructions, but how does the machine actually do anything? The source material talks about a universal rhythm that every single program follows.
Yes, the IPO cycle. Input, processing, output.
It sounds deceptively simple, doesn't it?
It is simple, but it's absolute. It's the heartbeat of computing. It doesn't matter if you're calculating a tip on your phone or playing a massive video game, the loop is the same. First, input. The computer accepts data.
This could be me typing on a keyboard, a mouse click, or even a sensor reading the temperature.
Right. Then, processing. This is the black box moment. The CPU takes that input and it executes the logic. It does the math. It calculates the trajectory of a bullet in a game or adds the tax to your bill.
And finally, output.
The result. It puts text on the screen, plays a sound, or saves a file to that SSD we talk about.
Let's look at the specific example from the source, because I think seeing it in code makes it real. They use a double the number program. It shows this in 3 different languages: Python, C++A, and Java.
Right. It's a very basic program, but it proves the point perfectly. Step 1, input. The user enters the number 5.
Okay, simple enough.
Step 2, processing. The code takes that 5, stores it in a variable, it's called mynumber, and then the CPU runs the math, mynumber2.
And step 3, output.
The screen reads, the doubled value is 10.
It's so simple when you break it down like that. But here's where it gets really interesting. Looking at the source code provided, in Python, the code is incredibly short. It's like 3 lines.
It's super concise.
But in Java, there's all this extra stuff. Public class main, public static void main, system.out.println. Why is it so different if they are doing the exact same thing?
This connects us to the lost in translation problem. You have to remember, the CPU, that worker at the desk, doesn't speak Python. It doesn't speak Java. It definitely doesn't speak English.
It speaks binary.
Machine language.
Yeah.
Zeros and ones. Electricity on, electricity off. They're the only language the hardware understands.
So everything we write, all that Python and Java, is just a convenient way for humans to talk. It all has to be translated.
Exactly. And this is where the source material dives into the great debate. Compilers versus interpreters. These are 2 different ways of translating human code into machine code.
Okay, let's unpack this. The notes categorize C++ and Java as compiled languages and Python as an interpreted language. What's the practical difference?
Think of a compiler, like a professional translator, who takes a book your source code and translates the entire thing from English to Spanish before letting anyone read it.
So all the work is done up front.
Correct. A compiler like in C++ or Java takes the entire source code file and translates it all at once. It generates a separate file, often an executable like an IDXE file.
Pros and cons.
The pro is speed during execution. Once it's translated, the computer can read that machine code incredibly fast. The con is that you have to wait for that whole compilation process to finish before you can even test the program.
And if there's an error?
Well, if there's an error on page 300 of your book, the translator stops and refuses to finish. They hand it back to you and say, fix this sentence. You can't run the program at all until all the errors are gone.
Okay, so that's the compiler. Now, what about the interpreter? The notes list Python here.
An interpreter is like a simultaneous translator at the UN. They are translating what you say live, line by line, as you say it.
So it happens on the fly.
Yes. The computer reads line 1 of your Python code, translates it to binary, executes it. Then it reads line 2, translates, executes.
That sounds slower.
It is slower overall because the computer's doing 2 jobs at once,
Yep.
translating and executing. But the advantage is you can run the program immediately. You don't have to wait. It feels much more interactive.
But there's a risk, right?
Huge risk. Since it's translating line by line, the program might run perfectly for 10 minutes. But if line 500 has a typo,
It crashes.
the program will crash right when it gets there.
That is a perfect segue into our next topic, errors. The art of being wrong. Because, let's be honest, computers are fragile. If I make a typo in a text message to you, you still know what I mean.
Right. Humans are great at context. Computers have zero intuition.
The source distinguishes between 2 critical types of errors: syntax errors and logical errors. Let's start with syntax. This is the grammar police.
Exactly. Every programming language has a syntax, a set of grammatical rules. In C++10, lines usually have to end with a semicolon. In Python, indentation is crucial. A syntax error is when you violate those rules. You miss a semicolon, you misspell print.
And the result?
The program generally won't even run. If you're using a compiled language, the compiler will yell at you immediately. It says, "I don't understand this sentence," and just refuses to build the file.
In a way, those are the good errors because the computer catches them for you. It stops you from embarrassing yourself. But then there's the other kind, the silent killer, the logical error.
These are the dangerous ones. A logical error means your grammar is perfect. You spelled everything right. The semicolons are in the right place. The computer understands exactly what you told it to do. But what you told it to do is wrong.
Like using the wrong formula.
Exactly. Let's go back to our double the number example. Suppose you were tired when you wrote the code, and instead of typing number 2, you typed number 3.
The computer doesn't know you wanted to double it.
It has no context. It sees the math, thinks, okay, multiply by 3, and it does it perfectly. The program runs, it doesn't crash, but the output is just wrong.
That is terrifying because the machine isn't breaking, it's just confidently giving you the wrong answer.
And it reinforces a massive truth about computers. They do exactly what you tell them to do, not what you want them to do. A logical error is a human failure, not a machine failure.
So how do we avoid that? I mean, if the computer can't catch our logical mistakes because it assumes we're smart, how do we catch them? This brings us to the blueprint section of the notes, the program development cycle.
This is where the source material tries to break the bad habit that almost every beginner has, jumping straight to coding.
Guilty. You get an assignment, you open the laptop, you just want to start typing.
We all do. It feels productive to type code. But the program development cycle puts coding at step 3. Step 1 is understand the problem, and step 2 is plan the logic.
Step 2 seems to be where the magic happens. The notes list a couple of tools here, flowcharts and pseudocode.
Right. Before you worry about where the semicolons go, you need to map out the logic. Pseudocode is great for this. It's just writing the program in plain English. Start, input number, multiply by 2, output answer, stop.
It strips away all the scary syntax and just focuses on the flow.
And flowcharts do the same thing visually. The source notes specific symbols. Ovals for start and end, rectangles for processes, diamonds for decisions. It's a map. If you can't draw the map, you can't write the code.
There is one technique in the notes that I found really fascinating. It's called desk checking.
Ah, yes. The lost art of desk checking.
It sounds like an audit or something.
It basically is. Desk checking is a manual simulation of the computer. You sit at your desk with a piece of paper, no screen, no keyboard. You create a table with columns for every variable in your program, like my number and my answer. Then you walk through your code line by line, pretend you are the CPU.
So line 1, input 5. I physically write 5 under the my number column on my paper.
Right. Then you look at line 2, my number 2.
Yeah.
You do the math in your head. You cross out whatever was in the my answer column, and you write 10.
It forces you to slow down.
It forces you to play the role of the machine. You see the data changing step by step. If you had that logical error we talked about, multiplying by 3 instead of 2, you'd catch it right there on the paper. You'd write 15 and go, wait a minute, that's not right.
And you catch it before you've written a single line of actual code.
Exactly. It's amazing how analog that is. To understand the digital machine, sometimes you have to go back to pencil and paper.
Before we wrap up, we have to touch on one last concept from the notes, paradigms. The different ways of organizing these instructions. The notes contrast procedural programming with object-oriented programming, or OOP.
Think of this as different management styles. Procedural programming, like the older languages C or Pascal, is a linear top-down list of instructions. It's a recipe. Step 1, step 2, step 3. It focuses on the procedures or functions.
It's basically a to-do list.
Exactly. And that works great for simple programs. But when you get to massive systems, like an operating system or a complex video game, a single to-do list gets messy. That's where object-oriented programming comes in.
And this seems to be the modern standard Java, Python.
OOP organizes code into objects, which are defined by classes. So instead of just a list of steps, you model the real world.
The notes mention properties and methods.
Right. So you might create a class called car. That's the blueprint. The blueprint says that every car has properties, traits like color, speed, model, and it has methods actions it can take, like drive or brake.
So instead of just a list of actions scattered everywhere, you're building these little distinct entities, objects that contain their own data and instructions.
Exactly. And once you build a car class, you can stamp out 100 different car objects, a red one, a blue one, a fast one, without rewriting the code for how a car works. It makes it easier to manage huge, complex programs.
It's like modular construction versus building everything from scratch every time.
That's a perfect analogy.
So what does this all mean? We've gone from the hardware brain, the CPU, and the volatile RAM through the universal rhythm of input processing output. We've seen how compilers and interpreters bridge the language gap and how syntax and logical errors can trip us up.
And importantly, we've learned that the coding part is actually the end of the process. The real work is in the planning, the flowcharts, the pseudocode, the desk checking.
It really changes how you look at the device in your pocket. It's not just a magic glowing rectangle, it's a rigorous logic machine.
It is. It's a machine that demands precision.
Hmm.
And that's the beauty of it. When you understand the logic, you stop being frustrated by the computer not working and start understanding why it's doing what it's doing. You realize the machine is a mirror of your own instructions.
Which brings me to a thought I want to leave our listeners with today. We talked about desk checking, that manual process of verifying your logic step by step on paper before hitting run. In a world that is increasingly automated, where AI can write code for us and answers are instant, we often skip that manual verification step.
We rush to the output.
Exactly. What would happen if we applied the rigors of desk checking to our real-world decisions? Before you make a big life choice, or send that angry email, or make that investment, what if you slowed down?
Pretended you were the CPU.
Right. Create the table, write down the variables, trace the logic line by line. If I do X, then Y happens. Verify the logic manually. You might find a logical error in your own thinking before it becomes a reality.
Because unlike with computers, in real life, there is no undo button.
Exactly. Sometimes the analog way is the smartest way. Thanks for diving in with us.
A pleasure.
See you on the next deep dive.